Hello, everyone. My name is Kevin Wynn, and today I'll be presenting my data analytics project. It'll be over global land temperature trends from 1900s to 2015. This project was part of my data analytics course, and I chose to analyze historical climate data to better understand how global temperatures have changed over time. Even though this is my first experience working with a large data set, I was thoroughly surprised with how much I could learn just by using Excel. So I'm going to go ahead and introduce a little bit of myself before we dive into the topic. So a little background about me. My name is, of course, Kevin Wynn. I am 32 years old. So I've had a chance to experience a whole number of things. I first attended the University of Houston back in 2012, graduating in civil engineering in 2016. From there, I had the chance to work a number of jobs as an EIT before I later joined the United States Air Force. From there, I served between 2019 to 2024. While I was there, I was working as logistics as in one of the logistics readiness squadrons. After completing my service, I decided to go back to school. Since the money was available from the GI Bill, I decided just to change of pace, do something different that I haven't done before. So I chose to pursue computer information systems with a focus on data science from Texas A&M Victoria, and I should be graduating in fall of 2026 as long as everything goes well and according to plan. And this project is part of that journey, and it represents my first real step into hands-on data analytics work, which is something I'd be interested to do in as I take a step forward into looking for new careers. All right, well, let's get into the meat and potatoes of this presentation. Now, we'll start with the research question. The project centers around one major question. It's how have global land temperatures changed from the 1900s into the 2000s? Now, I chose this question because climate change is a rather important topic in our society today, and I kind of wanted to explore the long term patterns using actual scientific data. Now, a lot of the things that we hear nowadays, it's more or less anecdotal. Every now and then, someone will publish a study, and sometimes the data is skewed. You can't really, well, you can tell, but it really comes down to how the data is framed. So I wanted to dive into it and kind of see for myself, see if there's any validity to the claims of how our climate's been changing. So keeping the question simple helped me design an analysis that was both manageable as a beginner, of course, and I wanted to have a meaningful conclusion for myself. Now, the data set that I'm going to be using comes from Berkeley Earth. I downloaded this data set through Kaggle. It's a combination and repackaging of about 16 archives gathered from NOAA's MLOST and NASA's JISC-TEMP data sets. Now, a few of the important details about this data set is that it starts from 1750, which is quite a long time ago. Now, we have the average land temperature data, but it's not until 1850 in this data set that we begin to incorporate minimum and maximum temperatures. And from that point on, the temperatures are also recorded monthly. And not only that, they start including uncertainty values, which is going to be helpful for this analysis because they're basing this data set with uncertainty values on information that is run through a 95% confidence interval, which tells us about the reliability of this data. And the uncertainty values are extremely small, usually just a few tenths of a degree Celsius, which means that this data set is considered scientifically reliable for a long term climate analysis. And here's an example, or here's a view of the raw data before any processing has been done to it. You'll see that it begins in 1750. We have our columns here indicating what each column is. And you can see that the first beginning data sets, I mean, of course, technology hasn't been up to par that early on. So you'll see that the ability to calculate uncertainties uh, or just identifying minimum maximum temperatures, they just weren't around at the time. And as we go deeper into the data, you see as we get into the 2000s, our data set, all of our columns are fully filled out. You see, like in column E, if we go back, you'll see that column E is land max temperature uncertainty. And following that, whenever we get down to these 2000 years again, you can see that all of our uncertainty values are extremely low. So this right here gives us an idea of how reliable our data is, how realistic it is to be using it for any meaningful analysis. So continuing on, the tools that I've been using, I chose to go exclusively with Microsoft Excel since it's readily available for us as students. And I've incorporated a few different formulas that were available and built into the library of Excel. Things that I've been using were equals year, where I can pass the arguments in as columns. And then I use average ifs. That's going to be useful later on whenever it's time to calculate yearly averages. I've also used pivot tables. Pivot tables are a great way to summarize data. You can select different columns and categories that you like, and it also has built-in functions that let you adjust the data values, whether you want the sum, you can input averages, and it lets you build line charts and go into regressions to kind of build a kind of mathematical sense of what that data is supposed to hold. And we'll also dive into trend lines and R-square values, so that way we can determine how closely our data and regression mirror each other. So preparing the data set, before analyzing it, I decided to remove all the years prior to 1900s because Excel does not really recognize dates earlier than that. If I were to try and change the type of the data to short date, the beginning date for that starts in the 1900s. And for the most part, since our data set doesn't start evolving until the 1850s, I found that it wasn't really useful to use any data beforehand. And as a note from Kaggle about the data set, mentioned that there were certain cooling biases and different technologies that have been developed over time. So the way that temperature was measured, it really changed throughout. We went from mercury thermometers to electronic thermometers, and just that advancement creates a lot of variability inside the data. And so to exclude that, I decided to pick something a little bit more recent. Keeping everything from 1900 onward makes the data easier to work with and more relevant to modern climate change. And from there, next, I would extract the years from each date and convert it into a numerical value in Excel so that way I could sort and group them properly for the pivot tables. The data set, if I go back and I can show you, the data set had all the dates as you can see in this format, and Excel reads that as text. So before being able to apply any of my formulas or functions to it, the data has to be of the correct type, otherwise we get a mixed match error. And finally, I reviewed the uncertainty columns. Since the uncertainties were extremely small, I mean, they were based on a 95% confidence interval. It gave me a lot of confidence in the accuracy of the data set. It tells me that the data is more or less true and there's not a whole lot of things that could have skewed the data that was gathered. Next, I'm going to using the pivot tables. The pivot tables, they're a great tool to simplify analysis. I use them to mostly calculate the yearly averages for average land temperature, minimum land temperature, maximum land temperatures. Now, pivot tables are extremely helpful because they can help you condense thousands of rows of data into clean tables showing one value per year is what I was looking for. Because the data that I am using, it went monthly, and it makes it just a whole lot easier to view over time going by a year to year basis. Doing monthly to increments are so small that whenever it comes to developing trend lines and looking at regressions, some of the data points they might seem so infinitesimal that it really flattens out our trend line, our curve. Almost makes it look like there's no change at all over time. Uh, and here's an example of what it looks like in Excel. You can see that I have functions to create pivot charts onto a new sheet. I mean, all the functions aren't fully shown inside this snapshot right here. If you scroll down, it gives you an option to produce a line chart, which I'm going to be showing you next. I've consolidated all the data and I created a line chart to make this a nice visual to be able to realize the data. You can see that our lines are all color coded. Now this thick solid line here, this is a representation of all of our data points from in yearly increments. You'll see as we go along. And then I've also included a line of regression using the trend line feature inside Excel. And along with that, you're also able to calculate the R square values, which in statistics they're called coefficients of determination. We'll go into that a little bit later in this presentation to explain what exactly that is and why it's important to analysis overall. But as you can see, just starting inside the 1900s, all of our base values are fairly low. Like our minimum temperature starts at 2 degrees Celsius, our highs are 13, almost 14 degrees Celsius, and you'll see that from where it starts in the 1900s all the way up into close to present day, still a decade ago, but 2015, I mean, the temperatures, in fact, definitely rising over time, which is one of the points that we wanted to prove inside this analysis. Now, understanding the trend line equations, we want it to show that there's some mathematical value explaining what exactly was happening. So if we go back, we see all of these slopes. These slopes are essentially our rate of change. That tells us the how fast we're warming. That's our warming rate. And as we can see from our data, you can see that the average temperature increased at about 0.01 Celsius per year. Our maximums increased by 0.009, and our minimums at 0.014. Now, judging from the math that was done, this means our nighttime temperatures are warming more quickly than daytime temperatures, which is a fairly known climate science pattern, which tells us that what we're analyzing does in fact fit the previous studies that have been published out there. Next, we're gonna go into explaining what these R values are, what these R squared values are. Now, the coefficient of determination, it measures how well the trend line fits the actual data points. And you can see from our results that our R squared value for minimum temperatures is 0.87. Basically, the closer you get to 1, tells you how strong that data, how that correlation is. And it's 0.87, that's telling us that it's very strong and it's consistent with the data that we have. It's a consistent warming trend. And likewise, you see average temperature is 0.72, so that's still fairly strong long-term trend. Now, when we get to the maximum temperature, you'll see that this number is much lower. It's 0.58. Now, it's not to say that the data points show no correlation. In fact, it just means that it does fit reasonably inside our line of regression. However, because of the fluctuation between our data points and our trend line, it gives us an indication that there's more fluctuations from year to year, but the pattern still trends upward. So it's not necessarily saying that our trend line is wrong. It's kind of telling us that there's a few more factors involved, or it could be several factors involved, that could have possibly affected why the data has those kind of fluctuations. And because that's not part of this data set, there's not really any greater reason to dive into it. Or as of yet, if you wanted to expand the study, that would be something to look into. But it's not necessarily essential for this analysis that we're doing now. Now, as a summary of the results of what we found out in this analysis, the overall data clearly shows that all temperature measures, the average, minimum, maximum, they've all increased significantly from the 1900s into the 2000s. Based on other geological studies out there and my experience in civil engineering, a few degrees difference is actually a significant change. 1 to 2 degree difference in Celsius is a matter of introducing droughts and other weather phenomenon into a local region. So seeing that change, it kind of eye opening. And we're also seeing that minimum temperatures have risen the fastest, which tells us that our nights are generally hotter overall. I mean, that means that our temperatures are staying warmer without the presence of the sun. So that's also it's an indicator for this climate change. And the trends remain strong even after considering uncertainty values in our data. So for most part, levels of uncertainty didn't affect the trends with our data. I mean, it's very reliable, and that gives me confidence inside this analysis that what I found out during the study was more or less accurate, and this analysis supports the conclusion that global land temperatures have steadily been rising for more than a century. So, next we go into limitations. There's a few limitations to this project, of course. The data set includes land temperatures only. Ocean temperatures weren't part of this analysis. As far as geology is concerned, ocean temperatures play a crucial role in weather and temperature in our world, as ocean currents can determine how low and high pressure regions interact with each other, and it can give us more insight into weather phenomenon as a whole. But for the most part, this data set is just mainly focused around land data. And Excel is a rather powerful tool, but is limited for advanced statistical modeling, and it's it's a little less inconvenient than using something like Power BI. And this project just identifies trends. It doesn't attempt to predict future temperatures at all. You can make assumptions based off the data that we have here that it might potentially continue climbing, but in no way is this a predictive model for that. Still, despite these limitations, long-term warming trends still remain clear and is well supported by the data that we were able to sort through and chart. Um, what I've learned in this assignment was it taught me how to work with large and real world data sets. I've had some experience with working with a lot of data in general as part of logistics, but those were within the spans of year to year. We're looking at fiscal year to fiscal year, and perchance looking at a couple of years at a time to assess budgets and resource allocations, but nothing on this scale to where I've had a billion data points spanning over centuries and decades. So getting a chance to work with large real world data sets was a new experience for me. And I've also gotten to see how important cleaning and preparing the data is. I mean, without cleaning and preparing data, it's really just a bunch of numbers. It's hard to make end to end points to kind of decide where to build your regressions, develop trend lines, and things of that nature. And using pivot tables was kind of eye opening, being able to quickly filter and summarize data using formulas in Excel. That's extremely handy tools, and I was pleased to have learned that in this project and experience. And um, I've gained more confidence when it comes to doing trend lines and interpretations. I've learned them before in statistics, but never really had to apply them outside of class. So this was a fairly good experience overall. I became much more comfortable in using Excel for data analysis, and I gained a better understanding of how data can really reveal long-term patterns. Uh, some final thoughts in conclusion. Global land temperatures have risen significantly over the past year, or rather centuries, and this trend is consistent across multiple temperature measurements. Using only Excel, I was able to uncover clear climate patterns and gain hands-on experience with real data. And I really enjoyed this class. I appreciate you for viewing my presentation. I hope everyone has a great rest of their semester. And yeah. I look forward to possibly working with you in the future if that ever occurs. But thank you again for viewing my presentation, and that will conclude this analysis.